Okay, it's time to go ahead and get started. Yeah. So, you can probably tell from what's up on the board that today's topic are K-maps. K here stands for Carnot, so Carnot maps. And the purpose of Carnot maps is to come up with reduced Boolean equations, either reduced SOP or reduced POS. Last class, those equations that we wrote, the SOP or POS, those were non-reduced because they came right from a truth table. Now, last time there was a handout, this handout on each of the tables. And remember, I talked about how there's these various laws and theorems. And, if you take a look at these, you'll notice that some of these are just like base 10. Like, for example, in base 10, when you're adding, order doesn't matter. Well, in base 2, when you're ORing, ORing doesn't matter. Okay? And you'll see other similarities with base 10 algebra if you pick up course with it. But De Morgan's, that's specific to base 2. No De Morgan base 2. Well, you could take these laws and identities and you can use them to reduce equations, reduce Boolean equations. Because you would see that you could factor out like common variables just like you can in base 10. Okay. So, you could do reduction of Boolean equations in a very similar manner than that you already know with base 10. But Carnot maps is sort of, at least some people feel, a fun way of doing reduction of Boolean equations. So, most people that teach this class, feel that Carnot maps, even though they're not used in practice anymore, if you go work somewhere and, you go to reduce some Boolean equations, you're going to use a program that does that. You're not going to, do a Carnot map. But I think, I feel anyway that it's good for you to know, because if nothing else, a lot of times computer algorithms are based on some of what's involved with Carnot maps. Okay? And like I said, I think this is a funner approach than doing more of a brute force like you would with a base 10 equation. Now, before I get to Carnot maps, there's just a couple things I want to cover before that. And one is this right here. You see this? Not A ANDed with not B is not equal to A and B ANDed, then the whole thing not. And the reason I put that up there is because that's a common mistake that people make. I mean, last time we talked about what a NAND gate is equal to. Do you remember what a NAND gate is equal to? That was part of De Morgan. Yeah, a NAND gate is equal to an OR gate with inverted inputs, right? This is an AND gate with inverted inputs. Okay, so just by knowing De Morgan's, you know that this isn't true. Okay, but you see, the reason I put this up here is, again, this is a common mistake. See, I see this mistake every quarter, unfortunately, and it goes like this. Let's say you're writing either an SOP or POS equation, from a truth table, and let's say, one of the terms is A, not B, not C. Well, this is the mistake I often see, is people will do this. Not the same thing. Okay, and I understand, like, sometimes it might be unintentional. You're like putting the dashes and they actually connect. Okay, but you have to watch out for that. Okay, because that's wrong. Okay, you would lose points on an exam if that happens. Okay, even if it was by accident. Okay, so you just got to be cautious of that. Okay. All right. The next thing is there's two other forms of representing, digital. We covered a whole bunch last time, right? Truth table, circuit diagram, Verilog code, all those things we talked about last time. Well, there's two other forms I didn't talk about, and the only reason I'm bringing them up now is because the activity today, which is on Karno Maps, it has these forms on that handout. In fact, you have, every table should have enough activity handouts for everybody at the table. So when you see these forms here, let's start with compact min. Okay, compact min, this summation sign here, sigma, is used. And then you can see there's a bunch of numbers inside parentheses. And then compact max, it has this capital pi symbol, again, with a bunch of numbers inside the parentheses. Well, compact min, this form here, it tells you where the ones are in a truth table. In compact max, the numbers inside the parentheses, it tells you where the zeros are. Okay? So for example, if we have this compact min and we then generate the truth table from it, and assuming that this is an 8-row truth table, we only go 0 through 6. So, it could be more rows, but it has to be at least 8 rows. So we'll just go with 8 rows. So say this is the truth table for this compact min. Well, these are the inputs where the output is a 1. So you can see I would just put a 1 here for input of 0. I put a 1 here, right, for an input of 1. I put a 1 here for an input of 5, and I put a 1 here for an input of 6, and then the rest would just be zeros. Okay, so the compact min form, it's just like shorthand for the ones in a truth table.
Aren't 5 and 6 the ones like higher, like the 1 0 0 and the 0 1, or 1?
So you're talking about where I put this one and this one?
Yeah.
Well, remember, just think of these inputs here as being like binary numbers. Like all zeros would be 0, right? And then 1, 2, 3, 4, 5, 6, 7. So that would be
Okay.
Yeah, we always start with 0. Okay, any other question about that? Okay, so now let's look at this compact max. And you can see here the numbers go past 7, right? 8 and 15. So it can't be a 3 input truth table, right? Because you only have 8 rows there. So, let's put this into a 16-row 4 input truth table. So again, if it's got the pi symbol, these numbers are telling us where the zeros are in the truth table. So there would be a 0 for 3, there'd be a 0 for 7, there'd be a 0 for 8, and then a 0 for 15. I'm sorry, I started to get at an angle here, sorry. Okay, but then all the other outputs would just be 1. You just fill in all the ones. Okay, so that's all the compact min and compact max are. They're just shorthand. One shows you where the ones are, the other one shows you where the zeros are. And I think the only time this comes up is for this activity because that's how it's described in the activity that you're going to do later on payments. All right, so any questions up to this point? Did I start recording? I did. Okay. My memory's been terrible. All right, so let's talk about K-maps. So first of all, in this class, there's 2 K-maps, an 8-cell and a 16-cell. And you may notice when you first look at these maps that it doesn't go in order, right? If you look at this row, it goes 0, 1, 3, 2, and then 4, 5, 7, 6. Down here for the 16-cell, the first 2 rows are the same as the 8-cell. Then it goes 12, 13, 15, 14, and 8, 9, 11, 10. Okay, so naturally, usually the first question somebody has about K-maps is why aren't these in order? Why is it numbered 0, 1, 2, 3, 4, 5, 6, 7? Why is this switched over? Well, the reason why it's the order that you see is because with this order, we get what's called unit distance. Okay, and what unit distance means is that for any cell, if you look below or to the side or above, in the case of the 16 cell, of any cell, there's only a 1-bit difference between the numbers for the cells. And these numbers for the cells are called indexes. Like index 0, index 1, index 3, and so on. Okay. So for an example of what I'm talking about is, let's say we look at cell 1 right now. Okay. All right, well, here's 1 in binary. Well, if we compare 1 to 0, right? If we compare 1 and 0, there's only a 1-bit difference between those two. If I compare 1 and 3, so 1 and 3, again, there's only a 1-bit difference between those two. If I compare 1 and 5, 1 and 5, again, there's only a 1-bit difference. And that's true for any cell. If you look to the sides or above and below, you only see a 1-bit difference. Now, it doesn't matter diagonally, and you'll see why later, but for any cell, to each side of it, or below it, or above it, there's only a 1-bit difference. And you see, if K-maps didn't have that property, if K-maps didn't have that unit distance property, it wouldn't work for reduction. Okay, so you see, if you add it 0, 1, 2, 3, right? Say this was 2 here. Well, if you compare, right? So say there's a 2 here next to the 1. Well, now if you compare 1 and 2, see, there's a 2-bit difference. See, that's not unit distance, right? So that's why you can't put the 2 next. Okay. All right. The other thing about K-maps that's good to know right from the start is, notice I put an A next to this row. I put a B for these 2 columns. That's what that line means. That B is for these 2 columns, and C is for these 2 columns. For the 16th cell, A is these 2 rows, B is these 2 rows, C is these 2 columns, and D is these 2 columns. Okay. All right. So why do we put an A here? Why do we put a B there? Why do we put a C? All right. Well, the reason why there's an A here is because if you look at 4, 5, 7, and 6 in the truth table, 4, 5, 7, and 6, these 4, A is equal to 1 for all those 4. Okay. Likewise, we could label this row not A. Because if you look at 0, 1, 2, 3, right? A is equal to 0 for all those. Right? See the reason why B is these 2 columns where we have 2, 3, 6, and 7? Well, look, here's 2, here's 3, here's 6, here's 7. B is equal to 1 for those. So likewise, these columns are not, right? Because if you look at 0, 1, 4, 5, you'll see that 0 or B is equal to 0 for those. Okay, and you see C, okay, which is your least significant bit. Well, for odd numbers, C, since it's the least significant, right, that would be the ones column. Well, since those numbers are odd, well, that's why C is 1 for those. Where for these, it's equal to 0. So those would be your not C columns. All right, so that's what these variables represent. This just tells you where the 1s are for A, this tells you where the 0s are for A, and so on. And it's the same for the 16th cell. For these 2 rows, A is 1. For these 2 rows, but not A, because A is 0. For these columns, C is 1. For these columns, C is 0. This would be B bar. This would be B bar. This would be B bar. Okay, so does everybody see how that works? Any questions about anything I've done thus far? We haven't utilized the K-map yet, but this is sort of like the basics of K-maps. Okay. All right, so now let's start to use K-maps to reduce equations. So the goal when you are using a K-map, the goal is to get the least number of largest groups. Okay, and you'll see that you can group 1s and you can group 0s. Whatever you're grouping, whether it's 1s or 0s, to get the most reduced equation, you want to get the least number of largest groupings. Okay. And these groupings can only either be square or rectangular. Okay, you can't have diagonal groupings. You can't have like irregular shapes. Okay, they either got to be rectangles or squares. And you can only group 1, 2, 4, 8, 16. You can't group threes. You can't group ones or zeros and threes or any other number other than 1, 2, 4, 8, 16. Okay. Now, if you have an 8-cell K-map and you make a single grouping, you just circle either a single 1 or a single 0 in the map, that's going to give you a 3-variable term. Okay, you're going to have 3 variables in your term if you just circle 1. And it's an 8-cell. If it's a 16th cell and you just circle a single 1 or a single 0, it's going to give you 4 variables in your term. Okay, if it's an 8-cell and you make a 2 grouping, it's going to give you 2 variables. If it's a 16th cell and it's a 2 grouping, it gives you 3 variables. An 8-cell with a 4 grouping gives you 1. No variable in your term. A 16th cell with a 4 grouping, you get a 2-variable term. Now, if you have an 8-cell and all your cells are 1 or all your cells are 0, well, that means your equation just equals 1 or 0. Right? So you see, this would just be, F equals 1 or F equals 0. And then, of course, for an 8-cell, you can never have a 16 grouping. There's not enough cells, so that wouldn't apply. And for a 16 cell, if you have an 8 grouping, you get a 1-variable term. And if you have a 16, in other words, all the cells have 1s or all the cells have 0, well, again, the output would either equal 1 or 0, depending on what your group. Okay, now I'm going to go through examples, showing why this is all true. Coming up with, again, this is just preliminary information. The other thing I want to show you before we get to the examples is how you fill in a K-map. Okay, so we have these cells, and now when we fill in the K-map, we're going to put into each cell the output that goes with that index. Okay, the output that goes with that binary number it's associated with, binary input. So you see, looking at this truth table here, for an input of 0, the output is a 1. So you see, I put a 1. Okay, the next cell, cell 1, is also going to be a 1. Okay, cell 2, 0, cell 3, 0, cell 4, 0, cell 5, a 1, cell 6, a 1, and cell 7. Right, so you see, inside each cell is the output that goes with that number, okay, that input. Okay, and you would do the same thing for a 16 cell. So here, we only have 4 zeros. So let's see. Cell 3 would get a 0. Cell 7 would get a 0. Cell 8 would get a 0. And cell 15 would get a 0. And then all the other cells would be 1. So that's how you fill in a K-map from the tree. All right. Let's see, I got to move the camera. Right? Let's move the camera. No questions at this point? Let's get all of this in here. We can go further. I think. We'll do this. I think that's good. All right, so as you can see, I've got a bunch of examples. Now, I didn't choose these examples like haphazardly, okay, just to make busy work during class. I chose each of these examples with a purpose, like each one shows you something. Okay, hopefully. Okay, we start off, kind of basic, and we kind of get more challenging as we go. So let's look at this K-map right here. Now, you can either group 1s or 0s. And remember back last class, right? We're just looking at a truth table, and you see, when you get equations from a truth table like we did last class, that's getting the non-reduced Boolean equation, right? Either the non-reduced SOP or the non-reduced POS. Okay. And remember last class, if we wanted the SOP for F, what did we look for in the truth table? SOP for F. You look at zeros or one, you want F. One. You look at ones, right? When we wrote the SOP for F, we were just taking or looking at the truth table, looking at what input corresponded to the one, right? We said, you know, this, or this, or this, or this, right? Do that. If we wanted POS for F, how did we do that from a truth table? SOP for not F, and since we want not F, what do we look at? Yeah, you look at the zeros, right? So you get the SOP for not F, and then you do, you know, the De Morgan splice, which ends up flipping everything, you're converting all the variables, and so forth, right? So that's what we did in the non-reduced case from the truth table. Well, from a K-map, if I want the reduced SOP for F, I circle ones. If I want the reduced POS for F, I circle zeros to get the reduced SOP for not F, and then I just do De Morgan's twice again, just like you do in the non-reduced case. But now you get the reduced POS, right? Because I started with the reduced SOP for not F. Okay, so you know, once we get our reduced equations, like everything's the same as what we did last class, right? The only difference is last class, those equations weren't reduced. Okay, it's the K-maps that allows us to get the reduced equations, again, in a fun way, at least some people. Okay, all right, so what we're going to do here is we're going to group ones. Okay, and you know, since I want to get the most reduced equation, my goal is to get the least number of largest groups. You see, the reason why it's the least number of largest groups is because if I have the least number of groups, that's the least number of terms, because each group gives me a term in my equation. And if I get the largest group, well, the largest group is going to give me the minimum number of variables in a term, right? And that's what we mean by a reduced equation, right? You want the least number of terms, and also you want those terms to have the least number of variables. So by doing this, we'll accomplish that. Okay? So what I do when I'm using K-maps is I just am thinking in my head, okay, we want to group ones. Well, do we have a group of 8? Well, clearly we don't have a group of 8 because there's only 3 ones there. You know, do we have a group of 4? Well, no, we don't have a group of 4 ones because again, there's only 3 there. Okay, so what would you group here? What would you first group? What group would you do? Again, the groups have to either be square or rectangular. 0 and 4. Yeah, 0 and 4, right? There's a 2 grouping, a rectangular grouping. See, I would group these 2 together. Now, since we're grouping ones, the equation is going to be for F. And now to get the term that this 2 grouping gives us, we look at what's common to that grouping. See, what's common to this grouping is this column here, which is not C, and also this column is not B. See, what's not common to this 2 grouping is A, right? Because for this one in this group, we got A. For this one in this group, this is not A. So you see, whatever variable changes for that grouping, that falls out. Okay, what you keep are the variables that are common. Okay, so you see, this 2 grouping is going to give us a not B, not C term. Right? Does everybody see how I got not B, not C? Because see, this is the not B, not C column. The not C columns here, not B columns here, and that's what's common to this 2 grouping. It's only A that changes, so that's why A drops out. Okay. All right, well, we got another grouping, or we got another one that we have to group. Like you have to account for all of the ones that you're grouping. So it's gonna be this term or the term that comes from this other one. And I can't group this one with anything else. So, or with any other one. So this is gonna be a single grouping. And when you have a single grouping, it gives you 3 variables because you just write the Boolean term for a 3. Right? So you see, this is just gonna be not A, right? Because you see it's in the not A column, or excuse me, the not A row, and then B, C, which is what you would write when you have a 3, right? Okay, so you see that's the reduced SOP for this P-NUM. So anyone have a question where I got this? All good? All right, let's go to the next one. And for this next one, we're also going to group ones. Now, the reason I chose this example is because this brings up that K-maps, they touch on the edges. Okay, so you see this edge over here and this edge over here, they touch. It's almost like this is like a ring, you know, and then you cut it and lay it flat. Or a cylinder, it's like a cylinder that you cut and then lay flat. So knowing that these edges touch, if we're grouping ones, what would you do?
No,
Or tell me the grouping first. How would you group it?
I'd make a rectangle and goes off with the edges.
Okay, so which cells are in your grouping?
0, 4, 2, and 6.
Right, yeah, because you can do this. You got a 4 grouping because these edges touch. And you see, you would want to do a 4 grouping, right? Because a 4 grouping is going to give you how many variables in that term? Just one. In fact, what is the only variable that's common to this 4 grouping? C0, right? B changes, right? Because these 2 are in B, these 2 are in not B. A changes, right? These 2 are in A, this is not A. So the only variable that's common is not C. Do you see why you wouldn't want to do 2 groupings? Right, because this is a common mistake in an example like this, is that people will group these 2 together, and then they'll do a separate number. It's like a bee or a bug up or something. It's after me. So a mistake that people often make is that they'll do a 2 grouping here and a 2 grouping here. But what is that going to give us? How many terms are we going to get? 2 terms, and each term is going to have how many variables? 2 variables. That's not reduced. This is a lot less reduced, right? Okay, I mention that because, you know, as you're doing these, always be conscious of what you're trying to accomplish, right? We're trying to get the most reduced equation. So if you have the least number of groups, that's the least number of terms. If you have the largest groups, that's the least number of variables. Okay? All right, let's do this one next. Again, we're going to group ones. Okay, so this one right here. So what do you want to group first? So it's a good idea to always start with the largest groups possible that you can do.
1, 3, 5, 7.
Yeah, 1, 3, 5, 7. There's a group of 4 that's a square, right? I'll write the equation here for that. Okay, so what term are we going to get from that 4 grouping? What's common to that 4 grouping? C. Right? C. All right, but we're going to have another term because we have this one that's not part of a group. Now, again, the reason I have this example is because you can overlap groups. So knowing that you can overlap groups, how would you group this one over here? Oh, well, why can't I do 5, 7, 6? Right, but remember, we can only do groups of 1, 2, 4, 8. So you can't do 3, but you could.
6.
Yeah, 6 and 7. Yeah, because you can't do 3 groupings, but you would include this one with the 7. So you would overlap this group. right? And you see the reason for that is because if I do a two grouping, I'm gonna get two variables in that term. If I just did a single grouping, I would have a term with three variables. That's not all the way reduced. Okay, so what's common to this two grouping? A and what?
B.
A and B, right? So they have A and B. All right, C would drop out because this one's in C, this one's in non C. So yeah, C changes, so it would drop out. Okay. All right, so everybody good so far? All right, let's do this one here, and this time let's group zeros. And since I'm grouping zeros, what is my equation going to be? Instead of F, it's going to be, since I'm grouping zeros, when you look at zeros in a truth table, yeah, it's going to be not F, F not. All right, so how do you want to group this? Could I do this? Could I group these four like this? No, why not? That's not a square or rectangle, right? That's some sort of irregular shape. So you can't do that. And you can't do diagonal. So what do you want to group? We're grouping zeros?
It's gotta be three different groups. 0 and 1.
Oh, okay, so you want to do 0, 1, so we'll do that. Okay, so from this 0 and 1 grouping, what term are we going to get? What's common to that two grouping? A naught, B naught. Does everybody agree? Right, they're both in the A naught row and the B naught column. Okay, so that's going to give us A naught, B naught. Oh, the other thing, by convention, when you write your reduced expression, always put them in alphabetical order. Now, it's not, I mean, it's logically the same if you don't put them in alphabetical order, but when you put them in alphabetical order, it just makes it easier to read, especially for the grade. Okay. All right, so what do you want to group next? 5 and 7, okay. And what is this grouping going to give us? What's common to this two grouping? C. Just C. A and C. They're both in the A row and they're both in C. But we're not done, right? Because this 0 over here is not accounted for. So how would you take care of this 0? Yep, because again, the edges touch. So you would put this with this here. And what term are we going to get? What's common to what we have here? A naught. A naught, C naught. Yeah, they're both in the A naught row and C naught. A naught. Does everybody see what I did there? Now, can you see that I could do a different three two groupings? Right, because what else could I do? Yeah, you could have done 1 and 5 along with 5 and 7 and 0 and 2, and I would still end up with 3 terms where each term is 2 variables. So the reason I point that out is because this example shows that sometimes a K-map gives more than one correct reduced equation. Now, what would not be correct is that you add another term. What not would be correct is that we have what we have here, and then we do another 2 grouping and write another term. Okay, that would be redundant because these zeros are already accounted for. Okay, so that's another common error that people make. Okay, they'll have a situation like this where you could possibly have 2 correct, most reduced equations, but they'll basically like combine the 2, if you will, and you end up with something that's not most reduced. Okay, so you got to watch out for that. Okay, does that make sense to everybody? Okay, so moving on. Let's do this one next, and we're gonna group ones. But what's different in this K map? What's here that you've never seen before? I don't think, unless you've taken a class like this somewhere else, but in this class, there's something we haven't talked about in this K map. This dash. Right, so see, this is the first time you've seen a dash in this class. What the dash is the dash represents don't care, doesn't matter, irrelevance. Irrelevance. Who's a good speller? What? Irrelevant. It's E-R-R-E-L. Is it another E than B-A? If that's wrong, I apologize. But anyway, when you have a dash, and remember, what goes in these cells are outputs coming from a truth table. So a dash means that that output, the value of it, doesn't matter. Like, you know, it's a 0 or a 1, but we don't care what it is. Like, it's not going to affect what we're doing. The most common example of a don't care output is an output that's not connected to anything. Okay, sometimes you'll have a circuit or you'll have some sort of digital device, you know, that has multiple outputs, and you're not using all the outputs. Okay, there's nothing that says you have to use all the outputs that are available. So if I'm not using an output, if it's not connected to anything, it's going to be either a 0 or a 1, but I don't care what it is. Okay. So when you're doing a K-map, the dashes, right, the don't cares, they're kind of like wild cards. You make the dashes, you make the don't cares equal to whatever's going to lead to the most reduced equation. So you make the dashes equal to a 0 or 1, whatever you want, but you want to choose the one that's going to lead to the most reduced equation. So we're grouping ones here, so we're writing an equation for F since we're grouping ones. So what would you make these dashes equal to get the most reduced equation?
4, 1, and 0.
Exactly right. I'd want to make this one a 1, right? Because if I make that a 1, I can now do a single 4 grouping. Where if that was a 0, I'd have to do two groupings. Right? And a single 4 grouping is going to give me just one term of one variable. 2 groupings of 2 is going to give me 2 terms of 2 variables, right? So again, you want the most reduced. And I make this a 0, because if I made that a 1, I'd have another term, right? Okay, so you see, by making this don't care a 1 and this don't care a 0, I just have a single 4 grouping. And what term is that going to give me? Yeah. Not equal, right? This 4 grouping has not equal. Okay. Okay, let's do this one. This one here, we're going to group zeros. Okay, so we're going to get not F. So we got 3 don't cares. We're grouping zeros. So what would you make those don't cares equal to? So you get the most reduced equation for not F. Yeah, just make them all ones. How many people were thinking you got to make something a 0? That's why I put this up here, because a lot of times people think that they have to make the don't care equal to what they're circling. Otherwise, you know, they're not doing it right. But yeah, there's cases where you want the don't cares to be equal to what you're not circling, right? Again, you do whatever you need to do to get the most reduced equation. So yeah, you would make these all ones. So we only have a single 2 grouping. What term are we going to get for that 2 grouping? What is it? Not A, not A, C, yep. Okay. You're both in the not A row and the not C column. All right, so those were, you know, 8-cell examples. If you understood these 8-cell examples, well, the 16-cell, it's the same idea. It's just now a single grouping is going to give you 4 terms. four variable term, you know, 2 grouping, 3 variable term, 4 grouping, 2 variable term, 8 grouping would give you a single variable term. And again, if you got all ones or all zeros, the output is just equal to a 1 or 0. All right, so let's start with this 16 cell, and we're going to group ones. Okay, so where are we going to start in this example? No groups of 16, no groups of 8s. What would you group? Edges touch. For 16 cell, not only do these edges touch, but also the top and bottom touch. It's like a sphere that you kind of split and lay flat. Okay, well, we're actually going to get to that, but can we do a bigger grouping first? I like to start with the biggest groupings and then work to the smaller groupings. Is there a bigger grouping than 4, 5?
4, 6, 12, 14.
Yeah. Right, we can do these 4, because again, the edges touch. So we have a 4 grouping. So we're grouping 1, so. Okay, so what term are we going to get from this 4 grouping? What's common to that 4 grouping? Say that again? Yeah, B, not D, yeah. Right, because these 4, they're in the B rows, and then these are the not B columns. Oh, am I in the way? Again, you can move, if you need to move over here, you're more than welcome to. I know hard, especially on that side of the room. All right, but then we could do, see, if I was doing this again, there's not one way to do it, but I just think it's a good idea to always start with the largest group just so you don't miss them. But yeah, once we have this 4 grouping, I would do, as Ava was saying, you know, this 2 grouping here, right? Because we would overlap this 1 in the 5 cell with what's in the 4 cell, so we get a term that has less variables, right? Because what term is this going to give us? This 2 grouping.
A not, C not.
So it's, you said not A?
Not A, B, it's not.
Does everybody agree? They're in the not A row, the B row, and the not C column, right? What's different is D, because this one's in D and this one's in not. So. All right, but we got 1 left. What are we going to have to do with this one? Yeah, it's just going to be a single one, right? You can't group it with anything. There's no other one touching it, right? There's no one over here, no one over here. So this is just a single grouping. You can't group it with anything else, because again, you can't do diagonal groups. So this would give us a 4 terminal or 4 variable term. So it'd be not A, not B, C, D. Okay. Are you having too much fun with these? All right, let's see. Let's group ones for this one. Okay, group ones for this one. Write the equation up here. This one is similar to the one you're going to have to do for the lab 1. I mean, it's not exactly like it, but it's somewhat similar. So what would you group first?
Seven, 55.
Say it again.
5, 7, 55.
Okay, yeah, we could do this 4 grouping, right? Why can't I group 5, 7, 13, 15, 9, and 11? That's 6, and you can't do 6, right? Again, 1, 2, 4, 8, 16. Okay, so what term are we going to get from this 4 grouping? What's common? We should get a 2 variable term.
DB.
Yep, B and D. B and D. Right? What would you group next? Just 12 and 14? Yeah, do the whole row, right? Because again, you can overlap, and again, you want the largest group, right? Because that's going to give you the least number of variables. So yeah, you could just do this. Because remember, groups can overlap. Okay, so yeah, this row. So what's common to this row? AB. All right, now what would we do with these two ones? Yeah, group of width 13 and 15. Right? So you see, we do another grouping like this. So you remember, you can overlap. Okay, and what term are we going to get here? What's common here? AD. Getting the hang of it? Like I said, this one's somewhat similar to part of what you have to do for lab 1. All right, so now let's group ones for this one. And we have a don't care here. So first of all, what would you do with that don't care? Would you make it a 1 or a 0? Yeah, make it a 1, because then you have a 4 grouping. What term are we going to, what term are we going to get from this 4 grouping? Yeah, BD, it's the same as what we did up here, right? We had a BD up here. Okay, so this is the reason why I picked this example, is because you see these corners? Corners touch. Okay, because remember, these edges, both top and bottom, side, they touch. So this is like a sphere that's split and then laid flat. Okay, so you can group the corners. It's a 4 grouping. And what's common to the corners? Not B, not, yeah. Okay. And then lastly, we can group zeros. Let's group zeros for this one. We got some don't cares. So starting with, this is going to be not F. Right, it's going to be not F since we're grouping zeros. So what would you do? Well, what would you make the don't cares equal to? And just make them equal to 1, right? Because if I make it a 0, I'm going to add a term here. Also, I would add a term here. So I would make these don't cares equal to 1. Right? You agree with that? Okay, so then what would you do next? Yeah, do this column, right? You got a 4 grouping right here. Okay. And what term is that 4 grouping going to give us? Say it again. C not D not. Yeah. Right, the C, this column is part of not C and it's also part of not D. Okay. And then we got one more 0 here to take care of. So what would you do with this 0? Yeah, again, edges touch, so you overlap it and combine it with that 0. And then what term is this 2 grouping going to give us? It's going to be what? Is it going to be A? A, B not, B. Yeah, A, B not, and B. Yeah, I agree. Okay. So are these fun? I think it's funner than doing it, like manually, brute force with those identities and blocks.
Can you use the don't cares both ways? You it as a 0 and a 1.
Yes. Yeah,
So,
that's what we mean by don't care, that you know, again, the most common example is that output you're not going to use. Well, that output, because it's binary, can either be a 0 or a 1. And since you don't care, you can make it whatever you want.
Okay.
Yeah. Now, I mentioned this, you know, I talked about this, you know, a little bit today. But again, just to emphasize, if you circle the ones, you're getting the most reduced SOP for F. If you circle the zeros, you're getting the most reduced SOP for not F. And then typically the reason you would want this is because now we can use De Morgan's twice, right? And turn this SOP for not F into what? POS for F. You know, again, you invert everything, right? Ands to ors to and. So the reduced POS for F, it would be, well, you tell me, what am I going to write here? That's what you said, right? Okay. And you're going to have to do this not only for the activity, but also for lab 1. Okay. All right. So any questions up to this point? If not, let me talk about lab 1 before you do the activity, because it's only going to take about 10 minutes or so to talk about lab 1. And then once I'm done with that, the rest of today, work on the activity. Once you're done with that, you can start to work on lab 1. You can't finish lab 1 today. It's in 2 parts. You'll be able to do most of it today, but you won't be able to finish it until Tuesday of next week.
So if your SOP is in reduced form, and then you get POS, it's the POS also reduced form.
Yep. Sure is. Yep. Yep. Okay. All right. So, well, any other questions before I put the screen down and talk about lab 1? Just take a minute for this to warm up. And again, I realize that resolution is not going to be great on the screen, but this is right on Canvas. Now, just about everybody submitted their lab 0 I saw this morning. So you all know where the submission is for your lab work, you know, under modules. But you know, if you haven't already, take a good look at all that's there under modules. There's all kinds of information, and you'll see that there are lab instructions, and this is the instructions for lab 1. So for lab 1, you're going to design a locked box. Okay, and the locked box has a 4-bit input. And that lockbox will open, and a 1 at the output represents an unlocked box. Well, it will unlock with these inputs. Right? So you see you're given the inputs. I guess there's what, like 9 of them where it unlocks, and the other ones it stays locked, right? So unlock the 1, lock the 0. So the instructions are: first, draw a truth table. So since there's 4 bits, how many rows are you going to have in your truth table? Right, 16. It's going to be a 16-row truth table. And then from that truth table, you want to determine the SOP and the POS equation. So since you're taking, you know, the data from a truth table to come up with these expressions, they're going to be non-records, right? Okay, so this is similar, or this is exactly what we were doing last class. Okay, then it says to draw a black box diagram. Okay, so what does a black box diagram show you? Like, what's the purpose of a black box diagram? Exactly, it just shows you the main inputs and the main outputs. So how many inputs? 4. And for right now, you're going to have 2 outputs. One output is SOP, the other output is POS. But then on Tuesday, I'm going to talk about NAND, NAND, and NOR, which are 2 other forms of logic circuitry. And after Tuesday, you're going to add a 3rd output, NOR. Okay, so for today, you got 4 inputs, 2 outputs, but by next week, Tuesday, before the lab is due, you're going to add an additional output. So you'll have 3 outputs eventually. Okay? All right, but then we want you to use a K-map to get the reduced SOP and POS, right? So it's just like what we talked about today, right? You're going to take your truth table, put it into a K-map. It's going to be a 16-cell K-map. And you want to get the reduced SOP, okay, for F. So what are you going to circle for the reduced SOP for F? You're going to circle the 1. And then how are you going to come up with the reduced POS for F? Circle the 0s to get the reduced SOP for not F, and then do De Morgan's twice, right? Which again is just converting everything ands to ors, ands. Okay? And that's what you're going to put into your code. See, you're going to build the circuitry on, in Vivado and on your board. That's the reduced SOP and the reduced POS, right? Because again, since this is all logically equivalent, you want to use the reduced expressions because that's going to lead to the minimum circuitry. So as far as today goes, and again, you would start this after you're done with the activity. You would approach this just like you did lab 0, okay? Like you follow the same process. Now in lab 0, how many outputs did you have? You just have 1, and you only had 1 Boolean expression, right? You use the assign, right? Well, here you're going to have 2 outputs, right? One is SOP, one is POS, and you're going to have 2 equations. So in your Verilog code, the design source, you're going to have 2 assigned statements. Okay, one for the POS and one for the SOP. Okay. In your constraints file for lab 0, how many switches did you have? 3. Here you got 4, right? Just 1 extra one. How many LEDs did you have in lab 0? 1. Here you're going to have 2 because you have 2 outputs. Eventually you'll have 3 after Tuesday. Okay. So this lab, as far as Vivado goes and what you do in Verilog, it's just a little bit more of an extension of what you did last time, right? Because you're going to have 2 equations, 2 assigned statements. And in your sim file, when you go to sim this to see if it's working 100% sim-wise before you download it to the board, how many test cases are you going to have? You're going to have 16, right? Because this is a 16-row truth table instead of 8 that you had for lab 0. Okay? So there's a lot of similarity to what you did last time. This is just like a little bit more of an extension. Now, what I recommend is that for every lab, you have a separate project. Like you create another project for each lab, right? So you got your project that you did for lab 0, create a new project for lab 1. And then you can just bring over, you can just take the constraints file from lab 1 or lab 0 and put it into lab 1, because that way you only have to edit it a couple things, right? You just got to edit 1 switch and edit 1 output. Now you might have to change the names, okay? But, if you've got something that works, it's good to reuse that. Like what I do with my sim file is that I'll copy and paste a previous sim into my next one, because I know the formatting is all good. I just got to edit the test cases and edit, like the file that's under test, and then also edit if I change the names of the inputs and outputs, to connect everything up. Okay, but sometimes I feel anyway, not everybody agrees, but sometimes I feel it's always good to use something you knew that worked previously and then edit that as opposed to starting all over again. Okay. Okay, so that's lab one. Like I said, you can't finish lab one today, but if you're able to get to the point where you simulate this, right? That your simulation timing diagram is successful for your POS and your SOP outputs, that's like 90% of the lab. So if you got that far before Tuesday of next week, you should be able to finish this lab by the end of class time on Tuesday, because if you have all this part one done, all you'll have to do on Tuesday is add another equation into your design source, add another output into constraints, run simulation over again, and then just download to the board. See, today there's no reason to download to the board. Okay, because you don't have the whole thing yet. You usually wait until you got everything before you download to the board. Okay, the last thing, and then I'm gonna let you go and start on your activity. I just wanted to make some general comments about troubleshooting, because over the weekend, I got quite a few emails from people that were running into problems, which I expected. And believe me, I like getting emails from students. But I wanted to point out, because I think a lot of those emails wouldn't have to be sent if you go to Canvas, and again, in the modules where all that information is, there's this general troubleshooting steps. Okay, so anytime you run into a problem, and I realize you're new to this, so you're like, oh my God, what do I do? But the general approach when your design is not working is that, first of all, does it fail before simulation? If it fails, like you can't get a good simulation, the problem is usually either in your design source or it's in your sim file, or it could be both. And if you're getting blue or red, when you do a simulation and you get your timing diagram, you're hoping for green. Green means good. Now, again, you still got to check the data, and make sure that the data is giving you what you intended from the truth table. But if you get red or blue in your timing diagram, that means there's like a gross error. Your data could be right, but something major is wrong. Things like an output or an input's not declared correctly, or maybe in your sim file, the part of the code after the file you're testing, and then the UUT, and then you start with the dot, a name of an input or output from your design source, then in parentheses, the name of your corresponding simulation input or output, right? Well, that's what's making the connections between your design source, input and output, and your test bench where it's going to test it. So like if something is wrong there, that can cause something not being connected, okay? So, red, blue, the thing you want to look at, if it's not simulating right, you want to look at both your design source and your sim file and make sure you have inputs and outputs declared correctly, and, things are connected. Okay, that's usually the cause of something like that. Now, it can be other things, okay, but that's usually the cause. If your simulation is good, right, you got all green waveforms and you check the data and everything matches your truth table, but it won't implement, make a schematic, or it won't generate a bit stream, that's usually the constraints, that something's not right with the constraints, okay? And the other thing I wanted to mention, because this is the most common thing, and believe me, this is annoying, I find it frustrating, and unfortunately, it's always been like this, in that computer compilers, when there's an error or warning, they give you like this cryptic description. Like the text is usually useless, okay? But what can be useful is sometimes, in fact, most of the time, when there's an error warning, it gives you like a link, like it will be in blue, and often it will have what it doesn't like it might say it doesn't like FLC_Q, and it'll have a link, and the link is usually to the file and the line number that the problem is at or near, okay? So, that at least narrows it down a little bit. I'm not always saying it's easy to find the error even with that information, but at least it's not like, where do I start? It gives you some place to start, okay? Also, sometimes with errors or warnings, it won't give you a link, but it will give you a path, like a file path name to like a log file, or it will tell you to type something in the window of the TCL message tab. And sometimes the information in a log file, or after you type in whatever it tells you to type in, is more useful. Okay, so, those are things that can help you at least, know where to look. Okay? Let's see, was there anything else that I wanted to say? Was there anything that you found doing the first lab that was odd or peculiar that you wanted to share, or anything, any error that like drove you crazy, what you found what it was? Okay, well, eventually you'll get one of those. Chances are. All right, well, I think that's all that I wanted to talk about. So what you would want to do next, like I said, is work on that activity. Everyone should have an activity sheet. Now, for this activity, there's 8 KMAP, but I want you to do 12 reductions. I want you to do 8 reduced SOP, and then I want you to do these 4, okay, the KMAP's on the right side of the paper. For these 4, I also want you to do reduced POS. Okay, so there's a total of 12. Okay, 8 SOP, 4 POS, and my answers are up there. Okay, in red are the POS.
So these.
Yeah, so those 4 you do both SOP and POS. Oh, you are? Okay, I got some. Sure.